Now we're on to part 2. And if we look at part 2 of the question, what we're asked for the relative acceleration of the particle relative to the wedge. So relative acceleration of the particle. Just to remind ourselves what relative acceleration actually is, I have a simple example done out here. Imagine that there's a moving floor, much like you see those moving floors at airports and so on, and the acceleration of the floor, we call it f. It's 3 meters per second squared. So imagine the floor accelerating to the right with this acceleration, and imagine a person or an object on the floor and accelerating to the right. They're moving to the right with an acceleration of 10 meters per second squared. Well, what we say in this example is that the person's acceleration, or what they think that they're going at, what they feel that they're going at, is 10 meters per second squared. But to an observer looking on from the side, of course, what's actually happening is the person is actually accelerating at 7, because the person is going to the left with 10, the floor underneath is going at 3 in the opposite direction, so overall the person is actually going with acceleration 7. So just to be clear again, the relative acceleration is 10 in this example, and the actual acceleration is 7. And this means in our question, when they mention relative acceleration, they're actually looking for A. And when they're looking for actual acceleration, of course, if they weren't looking for actual acceleration, we'd have to take into account the floor moving underneath. So we'd have to go to this diagram here. Okay, so part 2 of the question, find the acceleration of the particle relative to the wedge. To do this, we need to apply F equals ma 3 times and get 3 simultaneous equations. Part 2. So first we must apply to the particle the 3 kg particle in the horizontal and vertical direction. So let's do it horizontally first. Horizontally, what's happening? Well, by horizontally we mean along this x-axis here. So this is the forward direction down the plane. And what forces are moving forward? There's only one, 3g over root 2. So this is our force diagram, 3g over root 2. F equals ma gives us 3g over root 2 equals the mass, which is 3, times the acceleration. And this is where we've got to be careful. It's the actual acceleration, so we have to take into account the floor moving underneath. So the actual acceleration is a downwards minus f over root 2 acting against it. So we're looking at the horizontal component only first. A minus f over root 2. And we can get rid of those square roots by multiplying across by root 2, and that gives us 3g is equal to 3 into root 2a minus f. And that's the result, so we put a box around that. That's what we call equation 1, future reference. Now we must do the same vertically. Look at the forces in the vertical direction. F equals ma. And this object, looking on from outside, is actually moving vertically as well, because the wedge is moving underneath it. So it's actually moving down in this direction. And that's shown more clearly by the acceleration diagram over here. We can see quite clearly there's an acceleration component, f over root 2, moving in the minus y direction. So if we do the F equals ma equation for this, we see that in the y direction we have 3g over root 2 downwards minus r pulling against. So it's 3g over root 2 minus r. Is equal to ma, and the mass is 3 again, and the acceleration downwards is f over root 2. So the arrow in the acceleration, I need to really emphasize this here, because this is where people, I find, go wrong mostly in exams, with this direction here, getting this direction wrong. This acceleration arrow tells us the forward direction of motion. It's moving, 3 kg is moving in this direction, vertically, f over root 2, that direction. This means that when we come to the force, we have to take this force first, the force going in that same direction, which is 3g over root 2. So we take that first as our forwards force and r as our backwards force. So the net force is 3g over root 2 minus r, not the other way around. 3g over root 2 minus r equals mass times f over root 2. We put in our acceleration f over root 2 there. And multiply across by root 2, and we have 3g minus root 2 r is equal to 3f. And we call this equation 2. Now at this stage we'll see that we've got two equations and three unknowns. The three unknowns a, f and r. So we need a third equation to solve for these three unknowns. We need an equation in r. And we get that from the wedge. And we only need to consider the horizontal direction, because there is an r component in the horizontal direction. So for the wedge we just take F equals ma horizontally. And the only horizontal force on the wedge is r over root 2. So for the wedge, horizontally, F equals ma, and this gives us, as I said, r over root 2 is the force, is equal to m, which is 4, into acceleration, and the acceleration of the wedge in the horizontal direction, in the x direction, is simply f. And that means that r is equal to 4 root 2f. And there's our third simultaneous equation. And now it's just a matter of solving to find what we need, and what we need is the relative acceleration a. So we must solve those to find a. So let's list those three equations again. So the first equation is 3g, but actually those 3's also cancel, by the way, so it's just g equals root 2a minus f. That's equation 1. And equation 2 is 3g minus root 2r equals 3f. Is equal to 3f. And lastly, we've just proved, we put a box around that one as well, we've just proved that r over, it's actually done further, r is equal to 4 root 2f. That's our third equation, r equals 4 root 2f. And we call that equation 3.